Hi Year 11 and welcome to your fourth week of remote learning. This week we are focusing on closing the gap in your tectonics knowledge for paper 1. So today's lesson is just going to focus on the theory of plate boundaries and convection currents, and then we're going to apply all of that knowledge into an exam question which kind of fills the gap from your mock exam. So the first thing we're going to do today is we're going to recap the concept of convection currents. We're then going to apply that convection current knowledge to the theory of plate boundaries and margins. And then finally, we're going to have a go at an exam question. So start off with convection currents. You will see at the top of the page, there is a YouTube link. This is also attached to the class charts homework assignment you have been given. So you can open that up when I tell you to. The first thing I need you to do is create a diagram of the earth, which shows us the layers. So the inner core, the outer core, the mantle and the crust. And you are going to add in some arrows which represent convection currents. Then I'm going to ask you to use the labels at the bottom of your screen, which you can see in the black boxes dotted around the bottom. And I'm going to ask you to use those labels to create a labelled diagram of these convection currents. You can also use the YouTube video to help you with this task. So if you're working at a developer level and you are targeted and you are looking for a 3 or a 4, you are going to label the diagram with the given labels at the bottom. If you are working at sort of a 5 and 6 level, I want you to try and link the earth structure to the convection currents. So how is it that the inner core is responsible for the convection currents, and what features does it have that makes it responsible for that? And then if you are looking for a grade 7 or above, I want you to give some explanation which links the movement of the magma to how the plates will move in different directions. This task, I'm going to give you about 5 minutes, so to pause the video and time yourself 5 minutes to complete this task, and resume the video when you have completed it. Now that we've recapped our convection currents, we're going to move on to our second part of our lesson and our learning journey today, which is applying these to plate boundaries. Year on year, everyone struggles with remembering these, so I'm going to take you through it, I'm going to talk you through it, and you are going to make notes as I talk. I know that sounds a little bit boring, but sometimes it is the only way that we can address these misconceptions. So first thing I want you to do is get a page of A4, or if you are working on a computer, make a table and split your page into 3 columns like you can see on your screen. We are going to start with the constructive plate boundary. Okay, so first of all, I want you to create a diagram that looks like the one at the top of the constructive column. So you should have 2 plates moving apart with magma filling in that gap. The first thing that happens with a constructive margin then is that 2 plates move apart, and this can be any combination of plates. So it can be 2 oceanic, 2 continental, 1 of each, whichever, due to the convection currents rising and moving these plates apart on the Earth's surface. The second thing that happens is that because there is now a gap in the plates, the convection currents will cause the magmas to rise and to fill in this gap. This creates new land. It constructs new land due to the magma solidifying, which is our next step. Due to the fact that this magma is runny magma, it travels a lot further before it becomes hard and before it solidifies, which creates our nice and gentle, sloped, non-explosive volcanoes. As the plates jolt apart during the movement, this can cause really small and regular earthquakes. They don't tend to pose too much of a threat to human life. And if you are working at a grade 7 or above, you do need to know an example. And your example is the Eurasian plate and the North American plate, which creates the Mid-Atlantic Ridge, and it is how Iceland was formed. Moving on to destructive plate margins then, again, I want you to recreate the diagram at the top. Here you have a plate being pushed underneath another one, okay? So that is how you can create your diagram. So this part then, it is specific to which types of plates you have. For a destructive plate margin to occur, you have to have a continental plate and an oceanic plate moving towards each other due to the convection currents. The heavier and weaker oceanic plate will sink, or if you want to use the word subduct, it is even better, below the stronger continental plate, and then this causes the little bit of oceanic plate that's sunken here to melt. This creates really, really thick magma, really sticky magma that solidifies super quickly once it hits the Earth's surface. And as those convection currents cycle this new magma into the gap of the subduction zone, it bursts through and creates a really steep and dangerous volcano. Because that magma is super thick, It solidifies super quick on the Earth's surface, which means it builds up all these really steep layers, and that magma can get stuck in the magma chamber. So when it eventually explodes, it is really quite dangerous. And then for earthquakes, because the subduction pulls down on the plate here, pressure will build up, and when that eventually jolts out of place, it will release lots and lots of seismic energy, therefore creating really big earthquakes. Your example for this plate is the Philippine and the Oceanic plate. And then finally, the conservative plate boundary. This is where the two plates are moving side by side, okay? And it's really important to remember here is that they are either moving side by side in different directions or side by side in the same direction at different speeds. Again, these can be any combination of plates. These plates are not smooth, they are really jagged. So when they are moving alongside each other, friction will build up over time, and they will eventually get caught and they will get stuck. As the pressure between these plates then begins to build up, this will take over like 100 years, and eventually they will slip due to the amount of pressure that is there. When that happens, it releases massive amounts of seismic energy, creating really big and dangerous earthquakes. There are no volcanoes here because, as you can see, there are no gaps in the land. There is nowhere that magma can seep out. Land is neither created or destroyed. So there are no volcanoes here, only massive earthquakes. And your example for this plate boundary is the North American and the Pacific plate, the San Andreas fault line. If you look on the class charts assignment, I've put some more links on there for you of some more YouTube videos and some bite-sized stuff that if you're still a little bit stuck on some of these, you can look through and try and develop your understanding. Now, I know it seems like you've just sat and copied lots of stuff from the video, but it does help in terms of you have now got a concise step-by-step process of how these work, which will help you in our next part of our lesson, which is applying that knowledge to an exam question. So earthquakes occur at destructive plate margins or boundaries. If you see margins or boundaries used interchangeably, they mean the same thing. It is just where two plates meet. The image below shows a destructive plate margin. As you can see here, you've got the oceanic plate moving towards the continental plate. The oceanic plate is beginning to be subducted, and then it will be melted here into the mantle. The question is then, with the help of the image above, explain why earthquakes occur at destructive plate margins. So why do earthquakes happen when two plates meet and one is pushed below the other? So it is the same structure as always. It is a pedal. So we're going to start off with our point. Earthquakes will form at destructive plate margins because what is the plate movement? Okay, what is happening to those two plates? This will cause an earthquake because what will happen next? So we know that the two plates have met, they have subducted. What will then happen to this part of the plate? What will the interaction be here? What will build up? Now that interaction has happened, what will then happen as a result of that? So the pressure has built up here. What will then happen? And what does it lead to? If you can link this to the nature of the earthquakes, then that would be really good. Are they dangerous? Are they small? Will they cause massive destruction to human life? So your task is to have a go at this exam question using the sentence starters below. If you are developing, again, through levels 3 to 4, you can finish the sentences using the bold text to help you and my examples. If you want to get 5 or 6, you will include an example of this type of plate margin and link to how dangerous the earthquakes actually are. And if you want to be getting a grade 7 or above, you will need to have developed explanations of the processes such as convection currents linked to the movement of the plates. So in your point, you would link that those plates are moving together because of convection currents, and then explain what happens. Give yourself around 6 minutes for this question. So finally, bringing all our learning together, in terms of what you must upload, I want a picture of your annotated convection currents task, which links in with the first part of our learning journey to recap the concept of convection currents. And I want your completed exam question, okay? Because that brings together your knowledge of plate boundaries, which you did with me as we talked through it. And it will also show me that you can apply this to an exam question. Thank you for doing your home learning this week, and we look forward to seeing and marking your work.